Hello and welcome to our presentation on accurate and interactive visual-inertial sensor calibration with next best view and next best trajectory suggestion. Today, visual-inertial sensors are popular in robotics, self-driving vehicles, augmented and virtual reality applications. In order to use them for any computer vision or state estimation task, a good calibration is essential. In this work, we are interested in calibrating for the camera intrinsics, camera extrinsics, camera IMU extrinsics, and camera IMU time delay. Our main motivation for this work are guided by the fact sensor calibration is non-intuitive and often requires expertise. State-of-the-art state estimation frameworks such as OCVIS, VINS-Mono, and OpenVINS can in practice estimate the calibration parameters in real time. However, these frameworks require sufficiently accurate initial calibrations as well as sufficient visual-inertial measurements. Lastly, most popular calibration toolboxes such as Calibre, MATLAB, and OpenCV do not provide real-time feedback during data collection. Our objective in this paper is to provide users with an interactive graphical user interface that assists them in gathering informative visual-inertial sensor measurements. In robotics, the maximum a posteriori estimator is commonly used to solve the visual-inertial calibration problem. Maximizing the maximum a posteriori is equivalent to solving the sum of nonlinearity squares and can be solved using the Gauss-Newton method. Lastly, in this paper, we use the mutual information as a metric to find the next best view and next best trajectory for visual-inertial calibration. Our proposed calibration pipeline consists of two stages. The first stage aims to perform vision-only camera intrinsics and extrinsics calibration employing next best view feedback. In the second stage, camera IMU extrinsics are found by using next best trajectory feedback. In the camera calibration stage, the continuous search space in front of the calibration target is discretized with candidate next best views. Our calibration method then evaluates and suggests the next best view for the user to follow. Similar to the camera calibration stage, in the camera IMU calibration, we discretize the continuous search space with 6 trajectories and use mutual information to find the next best trajectory. To evaluate our method, we conducted 2 sets of experiments. First, we evaluated our calibration method in offline mode with a UROC dataset to verify our calibration accuracy is competitive against that of calibers without the interactive component of our system. Secondly, we conducted experiments involving a small batch of graduate students in calibrating an Intel D435i using Calibre and our interactive tool. We then used the calibration parameters from both in OrbSlam3 on 10 custom sequences and compared the estimation accuracy. Both figures show the box plots of the RMSE absolute trajectory error of OrbSlam3 on the UROC dataset in stereo VO and stereo VIO mode when running calibration parameters from Calibre and our method. The results show that OrbSlam3 yielded better odometry results on most sequences when using our calibration parameters in stereo VO, and all sequences when in stereo VIO mode. In our second set of experiments, we showed that OrbSlam3 performed best on 10 of our custom data sequences when using calibrations estimated using our tool by grad students, compared to using Calibre. Additionally, the median total time to calibrate the Intel RealSense was lower using our tool. To conclude our presentation, in this paper, our focus is on collecting informative visual-inertial calibration data. We did this by evaluating next best view and next best trajectories for the user to follow, and our results show that our tool was able to yield more accurate odometry results in OrbSlam3 compared to Calibre.